Work in thermodynamics. Now, the state of any thermodynamic system can be described with the internal energy. The internal energy of a thermodynamic system can be changed in two different ways. One can add heat to the system, or it can do work on the system. In 1845, James Joule presented his paper on the mechanical equivalent of heat. He was the first to discover that doing work on a system increases its temperature. A simple example of a thermodynamic system is a quantity of gas enclosed in a cylinder with a movable piston, as depicted at the right. Consider the work done by the gas during its expansion. When the gas expands, it pushes the piston outward. The pressure or the force of the gas is pushing in the same direction as the piston. Consequently, the work done is positive. Now let's make this a little bit more mathematical. Suppose that the cylinder has a cross-sectional area A, and the pressure exerted by the gas is P gas. The force exerted by the gas on the piston is the pressure multiplied by the area. When the piston moves up a distance delta x, and the pressure P is constant, the work done is F delta x, or P gas times A times delta x. But remember, A times delta x is just the change in volume, or delta V. Hence we can write work is pressure times the change in volume. W equals P times delta V. When the piston moves down, the gas volume decreases, so the work done by the gas is negative. So we write work done by the gas here is negative P gas times delta V. During the compression of the gas, the work W prime done by the external force is positive. So we write W prime equals the external pressure times the change in volume. The relationship between work done by the gas and work done on the gas can be presented as follows. Essentially, work done by the environment on the gas or externally on the gas is the opposite of the work done by the gas. W prime equals negative W. The relationship between work and pressure times change of volume can be represented as a graph of P as a function of V on what we call a PV diagram, depicted on the right. The work done is equal to the area under the curve on the diagram. So here we see a constant pressure changing the volume. And remember, P times delta V is work, and that too is the area under this line. In an expansion, the work done by the gas is positive. We have work equals the area under the curve equals the pressure times the difference between the final and initial volumes. In this case, because it's expanding, the final volume is greater, and hence the work done is greater than 0. Now, in a compression, the work done by the gas is negative. In this case, although the pressure remains the same, what we can see is that the volume contracts. It goes from the larger VB to the smaller VA. So the final volume is smaller than the initial volume, and therefore the work done by the gas is less than 0.